This is the introduction to 4DV510 data mining. I am your host for the next like 8 or 9 weeks, I guess. And this is the first thing I want to say is that this is the first time that this course is being offered ever in this university. So of course, even though I've tried my best to design an interesting course with lots of practical stuff and not much in terms of well, it's more I want it to be more geared towards programming and practical problem solving instead of too much theory, although we do have a little bit of both. But anyway, it's the first time, so obviously there will be some hiccups. There will be some things that maybe I have missed, or maybe I haven't planned perfectly for what's coming. So I just want to right now make sure that we have a completely open channel for discussion of the course. And I want you guys to know that every suggestion, every feedback that you have, criticism, ideas, whatever that you think could be done to improve the course and in any way, I am absolutely open to that. Okay. And because really it's a work in progress. Unfortunately, I mean, of course I spent a lot of time thinking about everything, but still it's the first time that it's offered, so it's impossible to avoid the fact that it is a work and still a work in progress in a way. But yeah, we will try and let's see how it works. And I'm going to start talking to you a little bit about what is data mining. And so the pre-requirements of this course include machine learning. So as in the other one with the individualization project, I expect that you have been doing some machine learning before, even if it's basic, but I expect that there is at least a little bit of understanding of what it means to extract information from data, right? Again, we're gonna build everything up from the bottom here for the course itself. I'm not expecting you to know a lot of stuff, but I just expect you to be fairly familiar with the process of simply like taking a data set and doing something with it. Okay, because I'm not going to start all the way from the beginning as if you didn't know what data was, right? So but then again, there are differences between machine learning and data mining. So of course we all know that there is a ridiculous amount of data out there, right? We all know that it is very, very cheap to store data. So yeah, what I meant was we all know that there's a lot of data out there. We all know that there is that it's very cheap to store data, so people are just storing data for no reason, just because maybe it could be used, right? But of course, the real deal is like, what can you do with it in a way that that you can make this completely well, most of the time this mass of data without any shape into something that you can actually use for some reason, right? But the real question I think that's important to answer, or at least to try to answer at this point in the beginning, is what is data mining and why is it not machine learning, and why is it not other things like statistical modeling or just database querying, things like that, right? So to be completely honest, I cannot give you like one concrete objective definition of what data mining is. It's a term that has been in a way thrown around since a long time ago, and that has been kind of like shaped or mixed up with other terms as you know, science and technology evolve and we understand better some things or other things, it started from in statistics, right? So in the beginning, statisticians would use this term data mining when they were doing analysis of large scale data sets and in different ways, right? So it started from that. And then machine learning came, and machine learning kind of also became a little bit mixed up with data mining, and it kind of like snatched a big deal, a big part of data mining, and kind of like took over, and that became machine learning. But and nowadays still it is possible to see to kind of like think of data mining as machine learning in a kind of a interchangeable way. But the truth is that there is an overlap between what we in this course, what we consider as data mining and machine learning, but they are not the same thing. So what I want you guys to think about when you're thinking about machine learning or data mining and you try to so for us in this course, the most important thing is that you think of data mining as something that's similar to machine learning, but not supervised machine learning, okay? Because we're not going to deal with supervised machine learning in this course. So we're not going to deal with classifiers, for example, or with regressions, or with things that are more like this idea of training a model in order to fit some kind of preconception that you have from the data that comes with the data itself, like labels or some kind of variable that you're trying to predict or something like that. The idea in this course is that we're going to mine the data for stuff that's in it and that we can extract from it, okay? Most of the time, stuff that we don't know about, that's unknown to us. There will be assumptions, of course, like you may assume that the data comes from a Gaussian distribution, for example, or you may assume that the data has clusters. Like I have a certain data set. I assume that this data has 3 clusters because I extracted it from 3 different places or something like this. And I expect that these 3 different places have different characteristics, so there should be 3 clusters in this data set. So there are assumptions. Most of the time you have assumptions, let's say, about the data, but these are assumptions that they're not based on the data itself. Let's say, like when you have labels or when you have regression, or a regression of a certain continuous measurement. So we're not going to deal with that specifically, in which is mostly what is done during a machine learning course. For example, you learn these things like how to train different types of classifiers, how to train different types of regressions, and then of course that's when the overlap happens. Is then when you in a machine learning course, then you have some kind of unsupervised machine learning, right? And that's when it gets mixed up with data mining. Now, unfortunately, let me wait a little bit. I guess my connection is not very good. I'm just gonna take a few seconds. All right. So, unfortunately, I don't know exactly what you guys have learned in terms of machine learning, because it's hard for me to assume. Some of you came from 4DV510, but some of you didn't. So there could be overlap with that one. And even though you came from 4DV660, to be honest, I don't know what are the contents of 4DV660 anyway. So I might take a look at that later next week, because I just got access to the materials today that I had requested before, because I wanted to prepare for that, but then I just got access to it today. So I might take a look at that next week, and then I might remove some overlaps and try to build upon that. but there will be some overlap because I cannot assume that everyone came from 4DV660, right? And so I will probably end up talking a little bit about some stuff that you already learned there. But in general, um, I want you guys to think that there can be overlaps, but we are not going to deal with supervised machine learning. Okay, we're only going to deal with machine learning algorithms if we do when they are algorithms that are extracting knowledge from data in an unsupervised way. Okay. It's also not purely statistical modeling, although there might be some of it. So some of the data mining algorithms have statistical underpinnings, right? Like when you assume that your data comes from a certain specific distribution, and then that informs your algorithms, that informs the way that that your algorithm works. Or you may have different types of algorithms for different types of distributions. So maybe if distribution is Gaussian or normal, you do one thing, and if it's not, then you do something else. That these things could be intertwined with the data mining algorithms. However, that is not a big, let's say, that's not like a requirement that you have a super clear understanding of statistics in advanced statistics or anything like that. Because in general, we will think of data mining more like an algorithmical process. So more like a programming. We will think of data mining as an algorithmical process, which means that even though there might be some math, some statistics, and some algebra, most of the time we're going to deal with algorithms. Okay. And of course, those of you who understand the connection between algorithms and math and statistics and things like that, you will say, well, they're actually the same thing. But that goes a little bit too far in terms of what we're going to see in this course. So from the point of view of our course, we're looking at things from an algorithmic kind of like perspective. So it's more like programming and less about formal math. Okay. Still talking about the overlap between data mining and machine learning. Machine learning works better than data mining when you have no underlying assumptions about the structure of the data and what parts of the structure will contribute to the solution, right? So what's the meaning of this? When you have a certain data set in machine learning and you're going to train a classifier or a regressor, you basically don't care about exactly how the features will contribute to your classifier as long as your classifier works. So if you don't have any assumption about how the features are actually helping or contributing to the final result, then machine learning works better, right? Because then you're ready. You just let the computer work out whatever combination of features that it has to do in order to train a good classifier. And then as long as the classifier is working, you don't care, and you not only you don't care, but you actually have no previous assumption about that. So then machine learning will work better. Again, you don't need to understand the solution as long as it works, and which is just exactly what I said. So, and then you have a specific objective cost function that serves as the goal of the learning process. Now, in data mining, you also have this sometimes, like specific objective cost functions that serve as the goal. You do have that in data mining also, but it's less clear cut than in machine learning. So again, if you're training a classifier, there is a very specific thing that you're trying to train, which is I want a new model that fits as best as possible the labels that I got. So you have this clear objective of where your model should go. Now, when you have data mining, for example, when you're training clustering or dimensionality reduction or extracting measures from a network or analyzing a data stream, while you do have some objective cost functions, they are not final. You cannot say, okay, there's this one specific objective function that basically is the only one you need, and then you don't need anything else. With data mining, that's not how it works, because with data mining, you might have 3 or 4 or 5 different things that you might be optimizing for, and all of them could offer you different perspectives from the data that are all interesting in their own way. So like, for example, when you have clustering, sometimes you can have a very complex data set, and then you can train 3 or 4 different clustering algorithms, and they may give you different partitionings of the data, which are all interesting in their own way, because very complicated, very high dimensional data sometimes don't have just one clear explanation to it. The patterns in very complex high dimensional data sometimes cannot be explained with one single final solution, right? Sometimes you have to look at them from different perspectives in order to see different important things from the data. And while, so again, while of course when you're training a clustering algorithm, for example, you might have some measure that is inherent to that algorithm and that will lead or direct the optimization. The point is that that is just one of the possible ones, and then you might have other ones that are as important as that one. So I want you, in general, for you to think of data mining simply as a set of tools and techniques for extracting hopefully useful patterns from large data sets, right? So, and again, of course, this is a very open definition, very broad, as I put in the slide. So, but that's intentional, because this course doesn't really have one, let's say, it's not a linear course in terms of having just one path or one aim and then just going towards that aim until the end of the course. It is actually, the course itself is actually centered around this loosely coupled collection of techniques that we're going to have. So we're going to have different techniques for analyzing different types of data, for example, and for extracting different types of patterns. And even though they are more or less conceptually connected to this idea of extracting patterns from data in general, they don't really have this super close connection to each other in terms of really giving this let's say a very concrete, very well-formed body of knowledge. So they are going to be intentionally, so the course actually is going to be intentionally a little bit diverse in that sense. So, but in general, that's what they are: set of tools and techniques for extracting hopefully useful patterns from large data sets. Okay, and of course they will, as you will see, they do share some concepts among the algorithms and everything, which is what we're going to see as the course progresses. So yeah, in other words, data mining is about discovering patterns, and it's interesting to think about what these patterns must, or these models must be, which is, well, they must be valid, right? So they must hold on new data with some certainty. I mean, if you're extracting some clusters from a data set and then you get some new data, then, I mean, if this new data that comes, it is completely different and actually ends up being like a completely different cluster, well, you should probably check if you're not overfitting, for example, on the existing data and so on. So even though, again, we're not doing, like, this is not supposed to be the kind of model where you can really just predict new data based on the previous one, like in machine learning, but still, if it doesn't work at all on new data when it should, then maybe it's not valid. It should be useful. So it should be possible to act on the item, it should be possible to make a decision in a way based on what you're seeing. So again, using the clustering example, if you have broken your data set down into three clusters, and that seems reasonable to you, then you can make decisions about this, right? You can make a decision that the elements of a certain cluster, they have some kind of similarity between them, which is higher than the similarity that they have with the elements that are outside of the clustering. So that kind of that can help you make a decision, right? For example, you know, in one of our recent papers, we had this problem where we had like 5,000 solutions to a certain problem that involves dimensionality reduction. And we want is to somehow communicate this to the user that instead of just choosing one final solution and then just giving it to them, like as if we were to say, hey, this is the solution to your problem, but that wouldn't be correct. That wouldn't be the right way to do it, because that was not the final solution to the problem. That was just one solution to the problem. And we want this to be able to represent this to the user, to say, look, unfortunately, I cannot give you one final solution to your problem because there are too many. But at the same time, we want this to give some solutions to the user in a way that the user could choose by themselves, right? So instead of so it's kind of like a trade-off. I'm not showing you all the solutions because we have 5,000 of that, 5,000, and I cannot give you just one because that would be oversimplified. So then we came to this trade-off where we said, okay, you know what? Let's cluster this data set into 25 clusters. So we just ran a clustering algorithm and we extracted 25 clusters out of this 5,000 possible solutions. And then from these 25 clusters, we took one representative solution. So we took one solution that represented that cluster in the best way. So one solution that was, let's say, the one that represented the cluster in terms of being the one that was closer to all the other solutions. And then we gave this 25 solutions to the user. So basically we say, okay, here are 25 representative solutions from this body of 5,000 possible solutions. And now you can choose which one of these that fits you the best with some other things. But what I mean is that we used it, right? We used the clustering in order to give us some let's say, summary of this data in order to use this in some way. And that's just one example. It must be unexpected, so it must be non-obvious to the system, which means it must be something new that you're gathering from this in a non-obvious way. If it's something that you already know about the system or about the data or the system where the data came from in terms of like general idea of a system, then that's not really interesting, right? Data mining must give you some kind of a new non-obvious knowledge, which is usually the case when you have large-scale data, because large-scale data, and especially if it's very complex and high dimensional, then there's very few things are obvious about it, unless they're like two super obvious clusters. They're like completely separated from each other, for example. And then it becomes kind of like an obvious thing where obviously there's two clusters, so you don't even need an algorithm to see that, let's say. But most of the time, what we want is to extract non-obvious things from data. And it must be understandable. So humans should be able to interpret the pattern. Again, this kind of sets it apart a little bit from machine learning, although research on machine learning has been moving towards interpretability very strongly nowadays. But the truth is that, objectively speaking, machine learning does not necessarily have to be human interpretable. Like, for example, the machine learning models that are pushing like an automatic car or how to say, a self-driving car on the street, they are very complex. They're incredibly complex, and the driver does not necessarily have to understand how they work. Someone must understand how they work, but probably someone who works on a Tesla or something, they must understand how the models are working, because if something wrong happens, they have to fix it. And also, if they want to improve it, they must understand how it works. But in general, the person who is driving the car doesn't necessarily have to understand how the models work. But when it comes to data mining, that's not really the case, because data mining is basically geared towards data analysts, and the data analysts must understand what kind of patterns they are extracting from the data, or else it doesn't, or at least they must understand like the results of the data mining process in such a way that somehow they can make a decision out of it, right? So, or else there's no real benefit from it. Just a small pause. How is it going so far? Is it horrible, bad, or medium in terms of the audio?
It's okay for me.
It's okay? Okay, good. Great. So let's go on. So I'm going to give you a very simple example. This comes from the book, actually. And consider that you have gathered a set of data points, and you assume that the data comes from a Gaussian distribution. Now, you have a bunch of points. You have a data set, right? So one very simple thing that you can do, again, assuming that the data comes from a Gaussian distribution or from a normal distribution, which sometimes you can be sure of this, and sometimes you cannot. So that's not a very easy assumption to make in many cases. But one way to analyze this data would be to create a model, for example, by extracting the mean and then standard deviation that best describe the original distribution from which the data was sampled. Now, this is something you can do in machine learning. This is something you can do in data mining. But what is the idea behind this is that when you do this, you're basically saying, hey, I have a data set, right? And I want to somehow extract something out of this. I don't have external labels to validate my hypothesis. I don't have anything specific that like gives me a specific goal to search. I'm just trying to fit the data or to try to find the best fit for the original data distribution as possible, right? So you can extract the mean standard deviation, and then basically what you did when you do this is that you have summarized your whole data set with just two numbers, right? So basically you have mean and standard deviation, and using the mean and standard deviation and using the normal equation that is the Gaussian that's so well known, you can basically reproduce this data set and then resample it if you want in order to generate new data points. They're going to be artificial data points, but if you assume that the distribution is correct, then they should be roughly close to the original. So basically what you did is you have summarized, you have mined these two parameters from your data set, and by mining them, you basically explain, so to speak, your data set using just two numbers. And maybe originally you had 100 or 1,000 points. And now you can basically recreate, so to speak, the rough shape of your data set simply by using two numbers. But of course, you're only using two numbers because that's how a Gaussian distribution works. But most of the time, it's going to be much more complex than that. The idea is just that you have your data, then you assume something about it, like it comes from a Gaussian distribution. Then you try to mine something from that. And in this case, you mined two parameters that allowed you to summarize your data set. That's just one very simple example. And it's interesting to understand that we don't have no specific objective use for the information that we extract. It's just some new knowledge that we got, and then we're going to use this to do something later. But it's not something that gives you just like a very clear-cut thing, like this is a dog and this is a cat or something like this, like what happens with a classifier, for example. Yeah, and summarization is one of the main applications of data mining. For example, one other common example is clustering, as we've been discussing so far. I like to use clustering as an example because it's a very clear and well-known application of data mining that most people probably have at least heard of. And we assume that there are, so when we're doing clustering, we again assume something about the data, right? Since before, in the previous example, we assumed that the data was coming from a Gaussian distribution. And when we do clustering, again, we're assuming something about the data. We're assuming that there are groups of similar elements in the data set. And we assume that these groups are forming somewhat cohesive groups, and that these cohesive groups have more in common with each other than they have with elements from outside of the cluster, right? So we can assume that that's not true always. You can't cluster every data set. Some data sets are just like shapeless blobs of high dimensional data. But still, when you do clustering, it doesn't matter, because when you run a clustering algorithm, even in a data set that has no clusters, the algorithm will give you clusters anyway, right? So for example, consider that you have a 3D data set that you have sampled from the surface of a sphere or something like this. Like you have a bunch of points on the surface of a sphere, right? And they're 3D, although it's a 2D manifold, but anyway, it's a 3D data set. So there you sample the surface of a sphere. Now, suppose you take a clustering algorithm and you say, hey, give me 3 clusters. So you're, for some reason, you don't know that these was sampled from the surface of a sphere, and you ask for 3 clusters. The algorithm will give you 3 clusters. These clusters will probably be like 3 areas of the surface of the sphere that are more or less, it will partition the surface of the sphere in 3 areas somehow, depending on the algorithm. And it will give you, okay, these are the 3 clusters that I found. And if you don't really interpret this in the right way, or if you don't really visualize this, or if you don't really understand your data well, you might think that these 3 clusters represent like 3 distinct groups of points in your data, but that's not true, because the cluster algorithms, most clustering algorithms, will give you results anyway. Doesn't matter if they make sense or not. So you see how that's one thing that I forgot to say in this previous slide. If your hypothesis is wrong, or if your assumptions about your data are wrong, then your model will also be wrong. So for example, in this case with the Gaussian, if the assumption that you have that the data comes from a Gaussian distribution is incorrect, so if the distribution is, for example, heavily skewed, or if it has like multiple peaks or something like this, then your model will be wrong, because one mean and one standard deviation will not be enough to explain the shape of your data. So these are things that we must always keep in mind, not because maybe sometimes you just assume, and sometimes you don't know, and you just make the best out of the situation. But it is important to keep in mind that most of these algorithms will assume something about the data, and if the assumption is not correct, then your results are not correct, and then you have to just keep that in mind as like a limitation of what you're seeing. It doesn't mean you shouldn't use it. Again, for example, even though the sphere does not have 3 clusters, you may want 3 clusters anyway. If you're aware that these 3 clusters do not mean that these 3 points are, that these 3 groups are completely separate from each other. But anyway, like for example, in my previous example, you need 3 representative points from the sphere. Let's say I want 3 points that are like equidistant from each other in the sphere, and they kind of, for some reason, you can use clustering for that, although probably you could do it in another way. But of course, considering that the data set is as simple as a sphere, so most of the time it isn't. But maybe you see, like for example, I don't care if there are 5 clusters in this data set, but I need 5 representative points from this data set anyway. So I will cluster it in 5, extract 5 clusters, extract 5 representative points from these clusters, and use them. And whether they come from 5 super separated clusters or not, in this specific case, it doesn't matter to me. So I use it anyway. So it's always, there's always this kind of like, you must be aware of it. It's not that won't give you a clear rule like use this or don't use this and so on. It's up to you as the analyst, but it's important to be aware that there are these assumptions, and that you must consider them when you do data mining, right? Yeah, one other common application is feature extraction. They use this term feature extraction in the book, but I think it's a little bit ambiguous. I'm going to use it now because it's in the book, but I kind of feel like it's a little bit ambiguous. But it's this search for salient structure in otherwise unstructured or too complex data. So it's basically like when you have raw data that you've extracted from somewhere, and you have extracted a bunch of features, or let's say the original raw features of your data, they come from some kind of a measurement that you did in real life, or maybe they came to you. It's already the way it is. So, or maybe, like, for example, the data comes from images, or from it's actually a bunch of audio files, for example, music or something like this. Then you've extracted some features from this that are the raw features, right? And this is not what we're talking about here when I talk about feature extraction. That's why I think it's a little bit ambiguous, because sometimes you can think of like, for example, you have an image, then you have pixels, and then you extract some features from those pixels simply by like representing them as RGB values or something like this. This is not what we mean by feature extraction in this specific case. In this specific case, we mean one extra step. When you take the raw features that you have, which are just like the raw numbers that you have measured, or for an image, like the raw pixels of that image, or for an audio file, the raw information that comes in audio files, which I'm not super familiar with, to be honest. And then you extract something from that. You extract, for example, if you have images, you can extract all kinds of things from an image in order to represent that image, right? You can extract like borders between objects, or you can extract, well, I'm not super also familiar with image processing, to be honest, but there are some features, some things that you can extract from the image by actually mining the data that's in the image, right? So you can then transform into something else, and then after you've done that, you have a data set, and then you extract features from the data set. So for example, in a network, you can extract measures from that network, right? Measures like betweenness, centrality measures, as they're usually referred to. You can extract centrality measures from that network that are based on mining the data that's in the network itself, right? And again, these, because we say feature, then it kind of feels like they're features, like machine learning features. But in this case, it's more like we're looking for salient structures in this otherwise unstructured and too complex data in many different ways, right? And for example, I say here that given a certain element, you might be interested in finding other similar elements or nearest neighbors. So you're trying to extract these little bits of information that are in the data but are hidden away, and then you can, for example, look for nearest neighbors of points, and that will give you a lot more information in order to do some other stuff with the data. In this case, it's more like a query by example, right? So query by example is like, okay, I have this completely crazy data set. I have no idea what's going on here, but I have this one example of data point that is interesting to me. So please find some other similar data that could be interesting for me based on this one thing that I have. And for example, that is usually like a recommender system, where you're watching a YouTube video and then you get other recommendations for other videos that you might watch, and that can come from the video itself. Like, for example, it can come from, well, the fact that if you're watching a video game playthrough, then maybe YouTube will show you other video game playthroughs because they're similar to the video that you're watching. But there's also another level to it, in a way, which is, well, actually YouTube will recommend the next video for you based on what other people who also watched your video are also watching other videos. So even though YouTube might not compare the actual content of the video itself, it can mine this data from other users who also watched the same video that you are watching. And in that sense, it would be like a network. It would be a completely kind of like a different type of data, or type of salient structure that would come, for example, from a network of people watching other videos that are being watched by the same people, so on and so forth. So these things are all things that we're gonna slowly look at throughout the course, like networks, data streams, clustering, dimensionality reduction, and some other things that are in the syllabus. And all these things are kind of like they kind of like fit together, but they also are slightly individual and will be investigated individually as we go. Yeah, and this term, for example, similarity, is something that will appear throughout the entire course for almost everything that we do, and there will be like many different types of similarity, as you will see, and depending on the data that you have different similarity measures and so on. There's something that's going to be very common throughout the entire course. Okay, guys, so basically this is it about data mining itself. So this is it about the introduction to the concepts of data mining. And I hope that I made it more or less clear about to you what is going on in the course. Of course, there will be more stuff to discuss later. But let's talk a little bit about the actual organization and how the course is going to be managed in a way, right? This is just I just put it here because I wanted to highlight the fact that you are required to have taken some machine learning course. So I expect that you have done some machine learning. It says on an advanced level, but I understand that, I mean, it's enough if you have some experience with machine learning at this point. There's always this English thing because we're going to do this in English. And the most important thing about the objectives that I wanted to highlight for you is that there are these two very important key elements that will be handled throughout the course, which is fundamental concepts against state of the art, right? So both things will go hand in hand. In every lecture, I will bring you fundamental concepts, like maybe stuff that is around for decades, because they are fundamental concepts that are always there and must be understood very, very clearly by those who are studying data mining. And then I will also bring a state-of-the-art view into it by bringing a couple of papers of things that have been done in the past few years and have made it into, let's say, the body of knowledge of the area more recently. Okay, so these two things will be coming hand in hand. And for the fundamental stuff, for the fundamental concepts, we will mostly follow the course literature, which is this book, Mining of Massive Data Sets. This is well, I think the most important things about this book is that, first of all, it's free and it's available online, so everyone can just go to the website and read it. Which is a good thing, because since there is required reading, I don't feel very comfortable in asking you to buy books. I don't know, maybe it's just me, but I kind of feel like that's kind of weird. So I prefer to use freely available books, unless there is nothing. So if there was nothing out there, then you would have to buy it. But since there is, then we're using this one. And it's a very good book. It's by, if you know a little bit about data mining, then you probably recognize the authors, because they are incredibly well-known and respected in their respective research areas. So Jules Leskovec is maybe the one, or if not the greatest authority network analysis in the world, and it's definitely top 5. Then Jeffrey Ullman is a monster in computer science. He has written many books that are used as fundamental literature in many courses, like compilers and all kinds of stuff. So these guys are really good. They're from now I may say something wrong, but I think they're from Stanford, even though the book is published by Cambridge University Press for some reason. but if I'm not mistaken, they are from Stanford. And yeah, the book is available online. You can go there. You can. There's a lot of stuff. There's extra material for reading. There's video lectures from them because they, of course, teach data mining courses using this book. And anyway, this book is very good. But at the same time, I do think that this book is sometimes a little bit, how can I say, it's not super pedagogical. Let's say it's not a kind of book that really like walks you through the subject very slowly and with care. It's kind of more like in your face book, right? They just throw a lot of stuff in your face, and it's like, this is it, this is that, blah blah. And so for that reason, I don't really agree so much with. I don't want you guys to just read the entire book completely from. I mean, you can, of course, if you want. There's absolutely no problem, but that's not what I will expect. Let's say when it comes to the examination in the end, I will actually give you as far in advance as I can the actual sections from each chapter that are the most important for you to read, because I'm also going to add some other stuff that's not in the book. So I'm going to kind of like juggle this thing. You're going to read a little bit from the book, and then a little bit from a couple of actual papers that are representing the state of the art in a slightly better way than the book. So just every week I will put the required reading and the exact sections that you have to read from the book, because I will filter them, and I will also I'm also reordering them, because I want to present the concepts to you in a slightly different order, not slightly, actually completely different order than what they're doing, because I think it works better in this way for us, for this specific context, right? But anyway, the book is great. There's a lot of stuff. Oh, and there's also one other thing that is different from when it comes to the book and our course, is that even from the name, you can see that it's mining of massive data sets, right? So there is this kind of perspective in the book where they are talking a lot about techniques for big data analysis. So techniques for some more advanced algorithms that will handle very, 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 very large data sets. Because the thing is that when you have data mining algorithms, you have the basic algorithm, let's say, that most of the time expects you to have the data in memory, for example. So you can the algorithm kind of expects that you will load the entire data set to the memory and analyze it somehow. So it doesn't deal with the fact that the data, for example, is too large to be put in memory all at once, or for example, it doesn't the fundamental algorithms don't deal too much with the fact that you have, for example, a data set that's so large that it sits in different computers in a network because it doesn't fit into a single computer, or things like that. Or sometimes, most of the time, it doesn't even deal with the fact that you may have to exchange data between the disk and the memory. So these things are kind of like abstracted away most of the time. But in this book, they do talk a lot about how to deal with these massive data sets when you can't really analyze the whole data set at the same time. In our course, we will not focus too much on that. I decided that I wanted to talk to you about the algorithms, to talk to you about the fundamentals, the state of the art, without mixing it too much with this other area, which is, analyzing large-scale data sets. I thought it was too much to mix these two things. We have a 5-credit course for 9 weeks, so it's not much, and we can't do everything at the same time. So I decided that we're not going to focus too much on this specific perspective of analyzing these massive data sets in a non-traditional way. Okay, there will be a little bit of that, and of course, if you're interested in that, we can talk about that, but that's not like the focus of the examination and so on. So basically, yeah, the fundamental concepts will come from this book. The state of the art will come from specific papers that I will provide to you. Hopefully not too complicated, but sometimes they will be a little bit complicated, which is to be expected. And yeah, so I'm going to actually go to the Moodle page and then go through the assignments, descriptions, and things like that. But for now, and I have some questions here that I actually already asked in the Moodle forum, and I realized that many of you have basic knowledge of Python, but would like to learn more. So if it's okay, if you're not comfortable with speaking because of the recording, you can also type in the chat. But I would like to discuss this with you a little bit about, first of all, because I saw some of you in the Moodle forums who said you're familiar with other languages, but I'm not sure if you intend to use other languages in the course or if you intend to use Python. So my objective question right now is, would you like to have access to videos where I am talking about Python and I'm talking about how to use Python in more advanced ways and how to like optimize Python code and things like that? Is this something that interests you? Would you like to have that? Like, if please individually, everyone say yes or no, and or type in the chat, just so I understand how many people would like to have that. Yes. All right. So most people want that. Okay. So because I've been teaching Python in other courses before this one, and I've got a set of recordings of many things, and my idea right now is that I will go through those recordings to see if they are if they make sense to you. If not, then I will record new ones. But probably I will take some recordings that I have from other courses where I was teaching Python and I was teaching like how to write optimized Python code and things like that, and then I will put them in my Moodle, and that will be like extra, you know, extra material for you, but it's not going to be required. So you can still use another language if you would like to. But of course, if everyone uses Python, that's much easier for us. But I understand that sometimes that's not possible. So okay, that's that. I understand that most of you want that, and I will do that. Now, so how about unsupervised learning? For you guys who did 4DV660, do you have unsupervised learning there, like clustering and dimensionality reduction and autoencoders and things like that? Did you see anything about that? Yeah. Yes, within R. Everyone used R in 4DV660? No? Yes? All right. I will assume that we need to go over the unsupervised learning again because anyway it's part of the syllabus for our course. Yeah. So just so I understand, you did see some unsupervised. You did do some unsupervised learning for DV660. Okay. Right. All right. So I will have to check then. I will make sure I look at the materials from 4DV660 to see how far you went into that and what was the literature to avoid duplicating too much. But I can already tell right now that there will be duplication because it is part of our syllabus, and like I said, I cannot assume that everyone came from 4DV660. So there will be some duplication, but I will take a look in order to just make sure that I don't that it doesn't become too boring. Also data cleaning. Did you also see stuff related to data cleaning in 4DV610? Data pre-processing and things like that. Okay, no values, elimination, and normalization. Not much. Okay, okay. Yeah, that's not going to be a huge thing. If it is part of the course, it would be nice to learn about dynamic community detection. Dynamic community detection. Yeah, that will, yes, that will come from in the lecture with for network analysis. It's one of the constants. Yeah, but when you say dynamic, do you mean like time dependent for networks? Yeah. Okay. Right. Okay, I'll keep that in mind. It feels like it's a little bit advanced for this course. I understand that maybe for your research it makes sense, but even if I don't deal too much with that, I can for sure dig up some stuff and send it to you, and then we can discuss that later, even if it's individually. And I'm not sure, it might be a little bit too advanced for the course, but I'm going to dig a little bit and see how it works. Now I'm gonna show the Moodle page so we can discuss some stuff from the Moodle. All right. Do you see my Moodle page? Okay. All right. So let's go through some more, let's say, boring, specific management stuff. As always, I guess by now you're used to it. This is the Moodle page. This is where the official communication will be done. So everything that's official is going to be on the Moodle page, and I also expect you guys to send me official messages through Moodle and not email or anything else. Although, again, of course, if you send me an email, I'm not going to completely ignore it, but I might not answer it as fast as I would if it was on Moodle. Okay. So I would prefer if we limit any other type of communication outside of Moodle, simply because I like things to be centralized. But of course, we do have the Slack channel. It's not official. It's just for you guys to talk to each other and discuss things. And I think it's a great communication channel. I'm just not following it too closely. So if you send me a direct message there, I may or may not answer it very, very fast. Okay, because I'm not following it all the time. There's this course schedule, which is I'm going to show you a little bit later. But let's talk about the course itself. So it's actually quite a traditional course in many ways. Like there's the structure of the course is quite traditional. There's not any kind of crazy different methodology or anything. So we're gonna have lectures. It's gonna be conducted online via Zoom, and it's also recorded and made available via my Moodle. So if you can't attend the lecture, the videos will be available to you in recorded. I want to ask you guys to be present in the lectures if possible, because I do want to have questions and I do want to have interactions with you, because with all this problem with the coronavirus and everything, I don't know, I don't want to lose this connection between us. I want us to be in touch. So if you can come to the lectures, I would appreciate it. And it's based on contents of the book and research articles that I will provide. There will be video tutorials. So these are pre-recorded and made available via Moodle. And this is the stuff mostly about the Python programming, which I just asked, and I was not sure if you wanted to have that, but you do. So I will make it available soon. And then there will be optional tutoring sessions, which is not meant, I mean, it's optional, but I also recommend you to come. And these tutoring sessions, the goal of this is to basically help you your assignments and your stuff. There's no, unless maybe we might need, like we might use these tutoring sessions to discuss something that needs to be discussed, like, oh, you know, there's this concept that was not very clear during the lecture, and it would be nice if we could have some extra lecture on that, or maybe there is some this specific aspect of Python implementation that we would like to know more about, and maybe we can use half of the tutoring session to learn about that. So it's very open actually. There's nothing planned specifically for that. It's the time that I will be available online to answer your questions, to help you with your assignments, and maybe to complement the lectures with something that might be of interest to you, right? So it's totally open for now. And like I said before, the goal of the course is to provide not only a fundamental introduction to the main concepts, but also some state-of-the-art. For the fundamental concepts, we'll mostly follow the book. It's freely available. There's a lot of material there, but as I have discussed, I have heavily reordered the chapters and sections, so I will provide them to you, specify them to you. Then there will be additional material, especially academic papers, which will be provided together with the corresponding lectures. So I will actually like put a copy of the paper on Moodle, so you can read it anywhere, not only when you're at the university. And then I guess what's most important for some of you, which is the course assessment. So first of all, there is one programming project that will span the entire course. The deadline for that will be October 30. And there's also a reflection report. The reflection report is going to be very short. It's kind of like this thing that we are required to do. So I will give you more details about it later, because I'm still deciding about exactly what will be the format and what will be the content of this reflection report. But I will come back to you like next week at most with more details about what exactly it's going to be in the reflection report. But basically, it's a written report where you have to write about the experiences that you had while developing the project. But I will specify it more objectively in the very near future. So next week at most. But there is one programming project that we will do during the entire course and then deliver it at the end. Then there's 6 shorter weekly programming assignments that will start from next week. These are really short, self-contained things that you're going to do. And I'm going to actually talk about the specific description of the weekly assignments in the programming project below, so I will not talk about it right now. And then finally, in the end, we'll have one oral exam, okay? And the oral exam will be, the content will be the required reading material. Whatever is posted as required reading material is going to be in the exam, okay? In the oral exam at the end. And I've scheduled both 29th and 30 for this, because I'm not sure how many people will be active all the way to the end, and then maybe we need to do it in 2 different days. But I hope that we can just do everything on one day, even if we have to book some extra time at that day. But let's see. And so I'm recording right now. Before we go to the actual contents of the weekly assignments and the programming project, late failed submission policies. The weekly shorter programming assignments can be delivered with a 1-week delay, but not later. Okay, so it's really weekly, and it's going to be a short assignment. So you couldn't do it in that week, then you can deliver it 1 week later, but then that's it for that specific assignment, right? Each of these will be graded, and of course, if you deliver it later, there's going to be a small impact in the corresponding grade. But then again, you can just you can make it up for that later with the other assignments if you deliver them in time. Then your final grade might not be affected that much. There will be a second deadline in November 30 to deliver new versions of the project and the reflection report. So since we have this deadline of October 30, then you have 1 month to deliver again the final things if you did deliver them in time, right? And again, of course, there will be a small, again, impact on the grade, but I will not restrict this. So anyone can send a new version on the second deadline, as long as you got a grade below B, because you cannot get more than a B if you deliver it in November. So if you got already an A or a B, then of course it doesn't make sense for you to deliver something else. But if you get a C on the first one, then you're absolutely free to try again to get and improve it and get at most okay, depending on what we discussed, depending on the feedback and so on. There will also be a second oral exam on the same day, November 30th. Tentative date. I will, if it doesn't work for someone for some reason, then we can of course change that. But at this point, it's on a Monday, and it feels like, at least so far, it's going to be more or less okay to do it this time, and I hope that not many people will need that anyway. So, and again, anyone can do that as long as you got a grade lower than B. You can try again and try to get it at this point. Okay, quite simple. There's not much, like, it's not like the other project course where there's all these millions of different things to think about. In this case, it's more or less straightforward. Like, it's more or less a straightforward programming course in a way, algorithm course, where you have to implement some stuff, like small stuff, self-contained, and then one big thing that will go through the entire course. This is the schedule. We are in week 36, the introduction. No deadlines this week. The next week, 37, we have a lecture and a tutoring. And no deadlines because, of course, at this point, you're going to start your first weekly assignment, and then you need a week to finish that. So the first deadline is actually going to be in 2 weeks, because then that's the final, the deadline for the first one, right? So maybe, I don't know if it's ambiguous here, but these deadlines here are not for the assignment of the week, right? It's the assignment of the previous week. So maybe I should make that clear here somehow, like weekly assignment 37, weekly assignment 38, or something like that. Just so it's clear that the deadline here is for the previous week, not the current week, right? Yeah, and then there's always a lecture and a tutoring. Now, one thing that I wanted to discuss with you, and maybe that's a very important thing to discuss, is that right now I had this lecture and tutoring, but I'm thinking that maybe it kind of does not work, because if you're let's say you start an assignment on week 37, then on Thursday, then by Friday you don't have anything, so there's no, the tutoring will be meaningless, and then on the next one, on the next Friday, it's also going to be meaningless because it's the day of the deadline. So I'm guessing that it might make more sense to have a tutoring. Either we have like tutoring on Thursday and lectures on Fridays, or we could have also tutorings on Wednesday morning instead of Friday morning. And the question is, do you guys have anything else on Wednesday morning? Any other course? That's what I wanted to know, because we have the lectures of the 4DV510 on Wednesday afternoon after lunch, right? So we could have these Friday tutorings on the Wednesday actually, and that means like you would get an assignment, then you would have, let's say, a few days to work on it, and then when you come on a Wednesday to the tutoring, you already have at least a good idea of what are the problems that you're having, and where you need help. Does that make sense? For you to be better or on Friday or Monday, okay.
What day is the deadline?
It's Friday. So you know you could have a tutoring on Wednesday and then a deadline on Friday.
For me, it's work perfectly.
Yeah, but Christian said it's better on Friday or on Monday. Yeah.
And
okay.
And if you move deadline to Sunday, would that solve?
It could be. It could be. Not sure if it would. I'm not sure if it would solve, because then you would have to work on a weekends. And I mean, I cannot expect that you will work on a weekend. And you shouldn't.
I love to work on the weekend.
You love to, okay, but I'm not sure if everyone has the same positive attitude. Next Wednesday you have decent meeting, otherwise it's okay. Okay.
Yeah, for me it's the same. I agree with Wednesday mornings, but anyhow, it depends on other students.
Yeah. So, okay, so Christian said it's not good for him on Wednesday. Does anyone else think it's not good on a Wednesday morning? All right, Monday. Maybe I could do it on Monday. Let me check. I'm not sure. But Monday, I'm not sure. It's Monday. Okay, guys, I will check my schedule later and think a little bit about that, and then I will confirm to you. Okay, yeah. Okay, Christian, that might work, but we could start at 10 and then you come at 11, and then if you need, I can spend a little bit more time with you later after it's over. But yeah, I will post this idea on the Moodle forum, because I'm not sure that everyone is here. I think everyone is here, but I'm not sure. But I will post this on the Moodle forums to see if anyone is opposed to this. But if no one else is opposed to this, I will probably move the tutorings to the Wednesday morning, okay? And then I guess it makes a little bit more sense that we do it like that. But I will let you know through Moodle to confirm if this is fine or not. And then basically we do this same routine until week 44, when there's the oral exam and the deadline for the project and the reflection report, basically. This final the week 43 here, which is 1 week before everything, the oral exam and the deadlines and everything. This week here, probably the lecture here will be an optional lecture. So it's going to be like a lecture that's not going to be in the oral exam, which means like some content that I will offer to you if you're interested, but probably will not be required for the exam, because I think it's going to be a little bit tight for you at this point. But we will have anyway some kind of optional lecture here with some content that is part of the course. But I will confirm to you exactly which part of which content will be that. But I can assure you that for sure week 43 will be an optional lecture. So okay, this is our schedule. You can see here that we have the required reading for this week up. Then I will post the required reading for next week on probably on Monday afternoon. Now let's go to the actual description of the assignments. Okay, so let's start with the weekly assignments. The weekly assignments will be self-contained, small-scale implementations of data mining algorithms. So basically, you're going to implement data mining algorithms. The catch here is that you have to do it from scratch. So you're not going to, you cannot use scikit-learn or any other library that has the implementations or may have the implementations already in them, right? You're going to do them from scratch without any machine learning library or framework. You can use any programming language that you want, as long as you provide instructions for me to run it, right? So if I can't run it, then it's a problem. And you might get a little bit of a downgrade in your, well, your grade could go down a little bit because, you know, it needs to be, I mean, I need to run it. I'm the examiner, so I need to run it. And but still, you can use, if everyone uses Python, that's the perfect world. I'm not sure if that's going to happen, but I will not be picky about it, because I know, you know, I know that not everyone has to use Python, or not everyone wants to use Python. But you have to give me some instruction. It cannot be something weird that I have to pay or something like this, because then that's, I mean, what's the point, right? So just to make sure that whatever you do when you submit it, you add a set of instructions, like you need to have this installed and that installed, and then you need to do this and that in order to run. And then hopefully things will be fine. You will be given some data sets with their expected outcomes. So whenever I ask for a certain algorithm, I'll say, I will give you a couple of data sets, and I'll say, okay, ideally, if you run it with this data sets, you should have this result and that result, or something similar to this. I always expect that there will be slightly different, slight variance in the results. I always expect that, and it's perfectly fine. But unless it's something that is very, very inherent to the algorithm, that the implementation, the results can vary, but they should be consistent. I mean, some are reasonably consistent. They must be. If they're not, then there must be a reason why they're not, and then we will have to discuss this individually in each case. But they should be reasonably consistent. If there are any random factors in the implemented algorithm, many algorithms have, then please provide a way to obtain reproducible results. So some kind of like a command line setting for specifying the random seed, or something that will that allows me to get consistent results if I run it a couple of times. Okay. Again, it depends on what you will implement and how you will implement. If it's going to be a command line thing, if it's going to have some kind of you know, interface, or any kind of interface that you will provide, whatever, it doesn't matter, as long as you give me some way to do it. Okay.
A question of clarity for implementing everything from scratch. Does that include also utilities like pseudo-random number generation and things like that? Or
no. Basic stuff from the language is okay. Just not anything that's related to the data processing itself, or the optimization and things like that.
Okay.
I will, when the actual assignments come, I will try to think as much as I can, to plan ahead as much as I can for this, and then to try to make it clear to you, like, okay, in this case, what I mean from scratch is this and that. But basically, it's just that you shouldn't use any kind of actual machine learning or data analysis library. You should do it from scratch. It's gonna, I guess, it has to be. I guess we will have to clarify this for each case, but I hope it will be clear most of the time. Like, for example, if you're using k-means, then k-means must be implemented by you, and not just calling k-means from scikit-learn, for example, something. And then you have, if you have a distance measure, then you have to also implement that distance measure yourself, instead of using it from when it comes from some kind of a ready-made library. So just the specific things that are related to the data analysis itself. Okay. Yeah, and then again, of course, if your implementation runs smoothly and generates expected results out of the box, then get an 8. But there are a few factors that can cause your grades to be a little bit low. Like, for example, if the results are too different from the expected without any reasonable explanation, they just don't work, and we don't know why, then I guess unless everyone says that nobody could get it to work, then maybe we can discuss that. But if some of you just, okay, it works, and then some of you, well, it doesn't work and I have no idea why, then it's for sure going to be a problem. Because I mean, maybe I give you an algorithm that is, I don't know, that maybe I managed to implement it, but no one else can implement it, then of course I will consider that. But if some of you can, so it's reasonable, and then some of you can't, and then so of course there's going to be a lower grade. The implementation only runs correctly for the 3 provided. Yeah, so I put 3 here, but I'm not sure it's going to be 3 all the time, but let's assume it's 3. The implementation only runs correctly for the 3 provided test datasets. So you make it run for the provided datasets, and then it doesn't run for anything else. Then of course it's going to be also lower grade. I cannot get the implementation to run even after instructions. That will be a problem. Please avoid that, because it gives a lot of headache. And I'm trying to be very open to let you use any programming language in order to help you. So please help me by making it very easy for me to run it. You have not implemented everything from scratch, and/or you have used code snippets found on the internet. So of course, plagiarism will not be accepted. If you copy paste something from somewhere else, and I realize that you did that, then I will not even correct it. It's just going to be an automatic failure for that specific assignment, and you will be notified of that. But if you use code snippets, then your grade will be lower. Like if you write a little bit of code and then you copy a little bit of code somewhere else, you're going to get a lower grade. Your implementation is too slow. Like it takes hours to do something that should be ready in seconds or minutes. Again, some algorithms are slow. So of course I'm not going to give a low grade for everyone because the algorithm is low, right? But if the algorithm is not supposed to be slow when it's implemented correctly, and again, it's like a reasonable thing. I will be reasonable in this. I will think, okay, normally this algorithm is not that slow, but then your implementation takes 5 hours when usually it should take 5 minutes. Then that's a problem, and you may have a lower grade for that. And the implementation is incomplete. So in case you don't manage to finish it, but you've done a part of it and you want to just submit it, it's okay. You get a lower grade, but you don't fail completely. So it's okay if you have not managed to finish it, to say, okay, I didn't finish it, but then you comment it a little bit and say, I went all the way to this point where I'm doing this and I'm doing that. And then I'm going to take a look at your code, and then I'm going to give you some grade depending on what is done. So what I mean by this is that if you have something incomplete and you want to submit it anyway, please do it, because it's better than like not submitting anything at all for the weekly assignment. Okay. So any questions on this one specifically? I expect that questions will come later, so I will be ready for that. Next one, programming project. So so again, this I forgot to say, but this weekly assignments, they will come together with the lectures, right? So I will maybe a couple of days before, but expect them to come together with the lectures, and then you have 1 week to do them after that. So, but usually they will come together with the lectures, because it's unreasonable for me to assume that you're going to do something before we have the lectures, and I'm not, let's say, allowed to expect that. So I'm going to provide them to you together with the lectures that are related to that specific concept. The programming project is this thing that's gonna be, you're gonna do it during the entire course, and then you're gonna deliver it at the end. It's a little bit of a meta test. So instead of while you're implementing the programming, or sorry, the algorithms in a self-contained way for the weekly assignments, and then they will be examined independently. So you get a grade for each assignment, and then finally you get a grade for the assignments in general. The programming project is assessed separately, and it's a meta test. So you will design and implement a data mining framework, which means that So what does it mean? It's like this. If you the weekly assignments, there is no requirement in terms of like the structure of your code, right? It's just code, and it must run. And if it runs and it generates the right results, that's it. I don't care about the way that you organize your code. For the programming project, I do care about the way that you organize your code, because the programming project is about actually having a framework. So in a concrete way, what is required from your framework? First of all, meta components or classes for specific concepts that we study in the lectures, right? So for example, you have a meta component for a clustering algorithm. And then this meta component kind of describes clustering algorithms. And then you can implement different clustering algorithms by extending or implementing this meta component. And then I say meta component or classes because I don't know which language you're going to use, but usually they're classes. So if you're using Python, for example, they're classes. Or if you're using Java, they're also classes. But I don't know, in MATLAB, for example, the ones who are using MATLAB, I don't know how that can be done, but we're going to have to use, or in R, but then we're going to have to somehow find a way to accommodate this. And I hope there is a solution. For example, so then there's a meta component for a clustering algorithm, a meta component for a network measure, a meta component to represent a stream, and so on. And the important thing is that eventual implementations of each of these concepts will be based on the meta components, so they can be assembled in a pipeline. So I can take any clustering algorithm, and I can take any distance measure, and then I can couple them together without them both knowing what is exactly the implementation of the meta components, right? So let's say I have a clustering algorithm and I want to test it with 3 different distance measures, then I will somehow use these 2 meta components together in order to build this pipeline, okay? You're gonna have to provide a few concrete implementations of each of the meta components, but differently than the weekly assignments, these concrete implementations of your component, they can be done based on existing libraries. So here, what you have to do is not really implement the algorithms from scratch, because you're already doing that in the weekly assignments. So in this case, you can simply like import scikit-learn and then use whatever is in there and then just kind of package them in your own framework. Or if you use MATLAB, you can import a toolbox that is already existing, and then you just kind of package it into your meta component or something like that. In Python, I mean, I say scikit-learn, but you could be whatever, PyTorch or anything that you're using. It's important part is that you package them into these meta components so that you can assemble this pipeline. And then finally, the final, let's say, goal of your framework is to have a mechanism for performing scripted benchmarks of different implementations of each algorithm in a specified pipeline. So since everything will be encapsulated in these meta components, then you can build these pipelines without actually specifying what is the implementation of each of these components of this pipeline, right? So for example, let's say I give you something like this. Create a pipeline where a data set goes through 1 step of dimensionality reduction, followed by 1 step of clustering. Then you benchmark which combinations of DR and clustering among a few specified ones run faster or with the highest possible quality. So for example, dimensionality reduction is one component, right? It doesn't matter which dimensional reduction it is, as long as it's a dimensional reduction that follows a specific meta component. And then, then you have clustering, again, meta component, right? And then you connect them together, and then you make a pipeline. And then you should run this pipeline by simply changing which dimensional reduction is considered, and then rerunning the pipeline or changing which cluster and so on. So by using meta components, you can do that. And this framework can also be implemented in any programming language as long as, again, I have the correct instructions to run it, okay? then again, guys, of course, if this all works well and everything's fine, then you get an A. But then, but it might happen that you don't because of some specific factors which are written here, and I would let you read it later because I'm going to run out of time, and I don't want to keep you guys too long. But what's important here is you will also get the specific requirements for the programming project as we go to the course, right? So, but so together with each lecture, I'm going to come to you with the weekly assignments, and I'm going to come to you with specific requirements for your programming project. But the difference is that the weekly assignments have to be delivered in 1 week, while the programming project kind of builds up. So I mean, if you don't have time to do it this week, then it doesn't matter to you. You can catch up next week. It's just that the requirements will kind of like accumulate as we go. And of course, if you manage to do them on time, then I guess it's better for everyone. But if you do it in the last couple of days, is also, I mean, it's up to you also. And basically, yeah, they are examined separately. So again, just to reinforce this, for the weekly assignments, it doesn't matter the structure of your code. For the programming project, it does matter. And of course, if you're smart, you could already build your weekly assignments inside your framework, because then you kind of like do both things at the same time in a way, and then maybe you can reduce the total workload a bit, because then you don't have to do them separately. But that, of course, that's completely up to you. And if you prefer to just deliver the weekly assignments in a completely messy way, that's okay, as long as it runs. And then later you can do the programming project. And with that, I conclude the introduction, as, I mean, in terms of the stuff that I'm talking about. But I can be open for questions now if you have any questions about the programming project or anything else.